So this is sidereal versus solar time, and I'm gonna have it run through 1 day on sidereal time. Here we go, which is 23 hours 56 minutes, and then the Earth needs to rotate another 4 minutes in order to point for the stick figure to point at the sun again. So watch, and I think that was really hard to see because it's only 4 minutes. So I'm gonna reset it. And this time, I'm gonna advance the sidereal time by 10 days, sidereal days. And let's say that the stick figure is looking at a star that is over here to its right. So 10 days later, and by the way, at this point, the stick figure is also pointing at the sun. So here, 10 sidereal days later, the stick figure is still looking up, still looking to the right to this star over here, but missing the sun. It's not pointing it. So it needs an extra, and you can see it's here an extra 40 minutes to get there. That would be 4 minutes on average per day. So I'm going to click here, and it needs to rotate a little bit more. So the Earth always needs to rotate an extra 4 minutes around it so that it can adjust from the rotation to a full day. And that's why the stars appear in the same place 23 hours 56 minutes later, while the sun needs extra 4 minutes because the Earth needs to rotate a little bit more. Since we are set on the 24-hour clock with the sun, that's why it appears to us that the stars are a little bit ahead every day or every night. 4 minutes going from one evening to the next. So the Earth is pointing at the moon away from the sun to the right, and the moon is going to orbit. And once it has completed one orbit, the arrow should be again pointing to the right. In this case scenario here, we actually do see a full moon. So let me run the animation. And I'm trying to stop it just as the arrow is pointing to the right. Right. I got it. I'm just short. I just cannot make it better. But notice pointing to the right, but definitely not away from the sun. And we can see that the phase is not full anymore. So let me run it another 27.3 days. That's how long it takes for one orbit. And again, I'm going to make the arrow point at the right, at which point the moon has completed another orbit. So here we go. And the arrow will point to the right as good as I can. Just a little bit short, but definitely way short of a full moon. And then again, another 27.3 days later. And so there, okay, this time I got it. See that? So this is 3 moon orbits later, definitely not a full moon anymore. That's why we have 2 numbers, because it takes another 2.2 days each time to make the phases complete. So I'm gonna totally start over here. So here's my animation for 1 moon orbit. Here, oh, a little bit too much. I tried it again. And I'm gonna stop here, and I'm gonna make the animation speed slower. Let me see if I can catch that. Right there. Very, very close. That would be 27.3 days, but I'm missing here to the full moon phase. So it needs to rotate a little bit more until here, where the arrow is pointing away from the sun and I have a full moon. But notice that's way beyond one orbit. The one orbit would be right here when it was pointing there. So that will take then a total of 29.5 days to go through phases. That's why there are 2 numbers associated with the moon's orbit, 27.3 days, and the lunar phases, 29.5 days, because as the moon orbits around the Earth, the 2 of them, of course, orbiting around the sun, and that's not negligible. I mean, that's almost a month. All right. So this is the time difference for the tides from one day to the next. So here we have, I just chose an arbitrary date and arbitrary phase of the moon. It actually doesn't matter. What really matters is that, of course, it's always the same moon. It always has the same mass, no matter what the phase is. So gravitationally, it affects us in the same way. But it depends on where in the sky it is relative to Earth in order to produce a certain tide. So let's say it has some kind of tide right here, and then 24 hours later, this is where the moon is going to be. So because, of course, of its orbit, it advanced quite a bit in those 24 hours, so it needs some more time in order to be in the same spot here above the eastern horizon, and that was about 50 minutes extra. So it takes 24 hours and 50 minutes to produce the same kind of tide because it needs to be in the same place. So again, another 24 hours later. And again, I need to advance the time. And that was actually almost an hour. It's not exactly 50 minutes all the time. On average it is, but sometimes it's 70 minutes, sometimes it's as short as 35 minutes, but on average 24 hours and 50 minutes from one day to the next to produce the same kind of tide. So this is about the year. We already know the answer, 365.25 days in the year. This is 10 days later. We see the Earth rotating here, and because the stick figure is still pointing at the sun, that's why it actually makes more rotation than the 30 days that we have so far, because it always needs to rotate a little bit more. Then I'm going to advance this one here. Notice the stick figure is actually always pointing at the sun. That's why the sidereal clock keeps moving, while the solar time actually goes like 24 hours at a day at a time, and we can't actually see that. So I'm going to do just a little bit short here. There we go. A couple more. There we go, and another 10 days here. Here's 360 days, so we're a little short of exactly 1 year, so I'm going to add those. I'm not going to go to exactly 365 because, unfortunately, this particular applet is going to go back to 0. So notice here, this would be here then 365.25 days to make one full orbit, while the number of rotations is actually exactly one more, 366.25 rotations. That's where the sidereal time comes in, where you keep adding 4 minutes every day, respectively. That's the difference between the two. And that's, 365.25 days in a year, where we, of course, take the 0.25 days over the course of 4 years to add a leap day. Makes calendar a little nicer.